is big news in the world of science. 4 new elements have been added to the periodic table, so I thought we should bring in our expert, Brielle, to explain what all of this means. From Salinas, California, please welcome back Brielle and her mom, Carrie. Hello, Brielle. How are you?
Good.
You look adorable. I love this dress. Is this a special birthday dress? It's your birthday today.
Yeah.
Happy birthday to Brielle. You're 4 years old today?
Yes.
4 years old? Do you feel different? Do you feel older?
No.
Okay, so let's talk about the elements. These are already, we already have these, right?
Yes.
What is this one?
Carbon.
That's carbon. And tell me something about carbon.
It has the highest melting point of all the other elements.
It does, the highest melting point of all the elements. And then what about this one? Oh, sorry. I have a puppy.
Lead.
That's lead. Tell me something about lead.
The ancient Romans used that to make their water pipes.
They did. The Romans made water pipes out of it. Okay. And what's this?
Fluorine.
Fluorine, exactly. What is this?
It's added to drinking water to help protect our teeth.
That is right. Now, if there was 4 new elements which were just found, and they're synthetic, right?
Yes.
Okay. And are they named yet or no?
No.
And do you think that you could name the elements? Do we have any pictures of the elements to show? So there's no name for that one?
No. And do you have an idea of what we should name it here? Well, this might help you. Tell Ellen why you have that for her.
I have something for you.
Oh, okay.
Why did you bring that for Ellen?
It's a mug. And did you draw this?
I did.
Wow, that's wonderful. And what does this mean right here?
Our new element.
Oh, it is a new element?
That's what she said that she wanted to name her element. Can you tell her what the name of it is?
Brielle. That's on the bottom.
Oh,
Ellen.
it's our names together, Brielle. Oh, that's a... And then
That's your drawing.
And then you did one like that, is that you and I together?
Yes.
Oh, I want that one too. I want both of these. I love these. There it is.
So you didn't see it back there.
I have a puppy. Well, I love this so very much. And did you do anything for New Year's?
We had a game night.
A game night? Oh, I heard about this. You played Heads Up, didn't you?
Yes.
You played Heads Up with the animal noises.
Yes.
And what animal noises did you... Oh, you're acting out the animal. Look at your dog. Your dog's like, what are y'all doing?
Yeah. Can you tell Ellen what your favorite animals to do were?
The cedar and the...
What's the first one?
The seagull
The seagull?
the cow.
What
Can
is
you show
this?
Ellen your cow?
I want to hear the...
Moo!
Ooh. And what does the seagull sound like?
I'm a bird, and I say, my.
Is that from Finding Nemo?
Yes.
By 1869, Mendeleev had been trying to find a pattern to the elements for a decade. Whatever order he and the world's chemists tried to impose, there were still elements that wouldn't fit. A universal theory seemed out of reach. But now Mendeleev hit on a new idea. He made up a pack of cards and wrote an element and its atomic weight on each one.
Strange though this might sound, so began the most memorable card game in the history of science. He called it Chemical Solitaire and began laying out the cards just to see whether there was a pattern, whether it all fitted together. Now, previously, chemists had grouped the elements in one of 2 ways, either by their properties, like those that react very strongly with water, or by grouping them by their atomic weight, which is what Berzelius and Cannizzaro had done. Mendeleev's great genius was to combine those 2 methods together.
The odds were stacked against him. Little more than half the elements we now know about had been discovered, so he was playing with an incomplete deck of cards.
He stayed up for 3 days and 3 nights without any sleep, just thinking solidly about the problem. Then on the 17th of February, with a snowstorm raging outside, he decided to stay at home. He was exhausted, and he finally dozed off.
The story goes he had an extraordinary dream. He saw almost all of the 63 known elements arrayed in a grand table which related them together.
It was an incredible breakthrough. I can imagine Mendeleev feeling like so many other scientific pioneers. It's that determination, even desperation to crack a puzzle, and then that eureka moment of revelation.
Mendeleev had revealed a deep truth about the nature of our world, that there is a numerical pattern underlying the structure of matter.
This is the periodic table as we know it today, and it's rooted in Mendeleev's discovery. It decodes and makes sense of the building blocks of the whole world. Now, although it's so familiar to us, it's on the wall of every chemistry lab in every school in the world. If you really look at it, it's actually awe-inspiring.
What's so remarkable is that it reveals the relationships between each and every element in order. Mendeleev had brilliantly combined elements' atomic weights and properties into one universal understanding of all the elements.
At its heart, science is about finding patterns in the world and explaining why they happen. Every field has them, but few patterns are as well known or as useful as chemistry's periodic table. In fact, it's so ubiquitous that we often think of a single, universal periodic table. Really, though, scientists have proposed all sorts of versions over the years, and some of them are stranger than others. But to talk about the periodic tables we don't use, we have to start with the one we do. There's one version of the periodic table you're probably picturing right now. Your high school chemistry teacher likely had it on their wall, and for good reason. The standard or long-form periodic table is really freaking useful. It's maintained by the International Union of Pure and Applied Chemistry, the worldwide body in charge of standardizing how chemists work. The standard table organizes elements into columns, called groups, and rows, which are called periods. The odd blocky shapes that result actually tell us a lot about the properties of elements and their relationships to each other. As the atomic number of the elements goes up, so does the number of electrons each element has. Due to their quantum properties, the electrons will occupy discrete positions known as energy levels. They're like shells that electrons fill in around the atom's nucleus. Every element in a period has a similar number of these energy levels, but those levels will be filled with a different number of electrons. Every element in a group, on the other hand, has the same number of electrons in its highest level, but might have a very different number of levels. That highest level is called the valence shell, and those outermost electrons are the ones that form chemical bonds. Sodium and potassium, for example, each have a single valence electron, and react readily with halogens like fluorine and chlorine way over in group 17. It turns out that organizing things into groups and periods like this reveals a bunch of useful relationships. Go down a column, for instance, and you'll find the atoms get progressively bigger. That happens because each element in a group has more energy levels than the last, and those levels are located farther from the center, kind of like the suburbs of a city. But slide from left to right, and the radius of the atoms tends to get smaller. That's because elements in a period have more electrons filling in the same energy shells and more protons pulling on them. After all, opposites attract. Most chemists probably don't remember whether gallium is bigger or smaller than indium, and maybe they don't even need to know that often. But it only takes a quick glance at the table to figure it out. That's the value of good organization. The standard table does have one weird feature. Parts of two rows, called the lanthanide and actinide series, are cut out and placed out of order at the bottom, which looks super awkward, but it's just to help the table fit on a standard piece of paper. The invention of the periodic table is usually credited to Russian chemist Dmitry Mendeleev. In fact, the UN has declared 2019 the International Year of the Periodic Table because it marks 150 years since his publication. And although we credit him with developing the table we use today, it's actually changed quite a bit since then. Mendeleev was struggling to make sense of the different properties of the elements, so he wrote each down on a separate card and ordered them based on their atomic mass, which is calculated based on the average mass of an element's atoms. Today's table is sorted not by atomic mass, but by atomic number, or how many protons an atom has. Elements can have different numbers of neutrons and electrons, but they always have the same number of protons. But Mendeleev had never heard of protons since they weren't discovered until the 20th century, so atomic mass would have to do. Mendeleev noticed that there seemed to be a repeating pattern when he arranged his cards by atomic mass. Elements with similar properties seemed to follow each other again and again, like an alkali metal always following a halogen. The noble gases hadn't been discovered yet, so they were skipped. He started wrapping these repeating or periodic patterns into rows and columns. The resulting table might not look like the one we all know and love, but many of its patterns remain today. Oxygen, sulfur, selenium, and tellurium, for example, all appear in a row in Mendeleev's notes. Our modern layout puts them together in a column. Mendeleev's great breakthrough was to leave space for elements not yet discovered. Based on where they should be, he made specific predictions about never-before-seen substances. He said, for instance, that chemists would soon find an element neighboring aluminum with an atomic mass around 68 and a very low melting point. In 1875, gallium was discovered, a metal with an atomic mass of 69.7 and such a low melting point that pranksters use it to make trick spoons. Modern chemists have discovered basically all the naturally occurring elements, so this predictive power is less important today. And we've made all sorts of other changes, so side by side, the two tables don't exactly look alike. But Mendeleev's table definitely matters. Science isn't just about cataloging what we can see today, it's about using that knowledge to predict what else is out there. An even earlier table was constructed in 1862 by French geologist Alexandre-Émile Béguyer de Chancrotois. Actually, table is kind of a stretch. His method wrapped the elements around a rotating cylinder. That might seem like a strange choice, but it reveals that Chancrotois was among the first to recognize the repeating nature of the elements. Using oxygen and its atomic mass of 16 as a standard, he divided the cylinder into 16 columns and placed each element in a column according to its mass. And he got the order at least somewhat right. As you turn the cylinder, you can see the familiar progression of lithium, beryllium, boron, carbon, and so on. His table became known as the telluric screw because the element tellurium was at its center. Like our modern table, elements in each column of the cylinder shared some common properties, but it was flawed. It included some compounds rather than just elements, and some elements were in more than one place. Still, the telluric screw could have been nearly as revolutionary as Mendeleev's periodic table, except for the part where it wasn't until later that anyone even noticed. The chemists of the day couldn't be bothered to read the work of a geologist. Plus, his paper didn't even include a diagram. The idea of a spiral table, though, has stuck around. In 1870, German chemist Heinrich Baumhauer constructed a 2D table that's much easier to read and store than a rotating cylinder. It was expanded nearly a century later by Theodor Benfey, with more elements and more colorful labels to aid interpretation. Supporters argue that the key feature of a spiral table is that it's continuous. Look at the standard table and you might think that chlorine and argon have much more in common than, say, argon and potassium. After all, they're right next to each other. In a spiral representation, though, it's easy to see that chlorine, argon, and potassium are three consecutive elements, each with one more proton than the last. Conversely, you might think that the lack of a gap makes it hard to see where periodicity actually repeats. It comes down to preference, but not a lot of people prefer the spirals. If you're looking for the periodic benefits of the standard table and the continuous nature of a spiral one, then Roy Alexander's 3D design is just for you. A museum educator from Brooklyn, Alexander in essence took the regular table and folded it back on itself, shaping each row so that it could connect smoothly to the next. The result is a design that connects every element to its neighbors, but also preserves the groupings many chemists find useful. Alexander didn't know it, but his table was actually very similar to a number of previous designs. Its most unique feature is that he convinced the US Patent Office to grant him a patent on the arrangement in 1971. Not bad for something designed in part by nature. Odd as they look, these designs do address one other concern. They bring the poor orphan lanthanides and actinides back into the fold. The table that's had the most influence on our modern version was probably the one put together by French engineer Charles Genet around 1928. It's often called the left step table, and it's a particular favorite of physicists. When read from top to bottom and left to right, it gives the exact order in which electrons fill up an atom's available energy shells. If you have to deal with electron configurations a lot, This is a big deal. Knowing how many electrons an element has in its energy levels can help predict its chemical properties, and some of its physical ones as well, like its magnetic behavior. So actually, having a handy reference for how an element's energy shells fill up is useful for a lot of scientists. Each shell has one of several basic shapes, and every shape can hold a different number of electrons. Like many things in science, for historical reasons, the shapes have confusing names. The first four are called S, P, D, and F. As electrons get added to an atom, they fill up shells with these shapes in a specific order. The first two go into an S shell, the second two go into another S shell, the next 6 go into a P shell, and so forth. Different shells correspond to different energy levels. You can see how this would all get very confusing very quickly. You can get this information from the standard periodic table, but it's not the main organizing principle. Unlike the left step table. Each block represents one of the basic shapes. The rightmost is the S shell, the next over the P shell, and so on. So if you want to know the electron configuration of, say, oxygen, it's easy to find by reading off each subsequent row. 1s2, 2s2, 2p4. So much easier. To convert the left step arrangement to the standard table, all you have to do is shift the S block from the left side to the right and move helium to be next to hydrogen, which makes sense if you're thinking about electron configurations. Hydrogen is 1s1 and helium is 1s2. That might seem like a small change, but people will probably tinker with a periodic table forever. In 2006, chemist Eric Sherry proposed a new table based on the left step design, but a touch more aesthetic. His table is based on the idea of chemical triads, or groups of 3 elements that share similar properties. First noticed in the early 1800s, triads might be the earliest known indication of periodicity. What's very cool is that if you average the mass of the lightest and heaviest member of a triad, you almost always get the mass of the middle one. For example, lithium has an atomic mass of 6.94, and potassium a mass of 39.1. Average those together and you get 23.02, just a hair more than the mass of sodium, which also shares some properties with the other two. These days, triads aren't that important because, we know the mass of sodium, but before Mendeleev and before the full discovery of periodicity, they had a certain predictive power. Sherry argued for a return of triads partly because they're elegant. They make a table that looks very orderly. It aligns as many triads as possible, including creating a new one of hydrogen, fluorine, and chlorine. Now, are the aesthetics that important? Probably not. After all, the table is just a convenient way of organizing elements. But it does reflect what scientists have been doing for more than a century. Before even Mendeleev, physicists and chemists have been trying to make sense of the ways elements are alike and different. Our modern periodic table manages to convey a bunch of those patterns. It organizes a tremendous amount of information, from trends in mass and size to reactivity and even states of matter. But once in a while, someone decides to tinker with it. And that's a good thing, because it reveals new patterns and serves different needs, or at the very least, gives us some pretty nifty shapes. Thanks for watching this episode of SciShow. We couldn't do what we do around here without the help of our Patreon supporters. If that sounds interesting to you, check out patreon.com/SciShow.
Inside this labyrinth of pipes and chambers, super heavy elements are being fused into existence. This machine is part of an international hunt to unlock the mysteries of this new class of elements that typically don't exist here on Earth.
Pushing these element discoveries really is pushing into models of how matter is formed in the Big Bang. How do we model matter, and how do we model the formation of the universe?
Super heavy elements exist for a fraction of time and are nearly impossible to catch. But understanding them could force us to reimagine the most iconic scientific symbol of all time, the periodic table. In 1869, Russian chemist Dmitry Mendeleev laid the foundations for what would become the modern periodic table. He arranged the known elements in order of increasing atomic weight, starting with the lightest ones with the least protons and working his way up. And as he did so, a curious pattern started to emerge.
What happened is he noticed that at regular intervals, chemical properties were repeating themselves because of this periodicity in the chemistry. He realized that there were elements at that time that had not yet been discovered, but should be there.
In the following years, scientists started isolating the elements Mendeleev predicted from various materials. Scandium was found in a hunk of euxenite, gallium in a piece of zinc ore, and hafnium in a zirconium mineral, to name a few. The table's design was revised and perfected as more elements were added. But as nuclei got heavier and heavier, finding them became a bit more complicated.
When we refer to heavy elements, we're talking about things that have these very large nuclei that have a lot of protons in them.
Above uranium, nothing exists here naturally. They have more protons in their system than anything that we have naturally occurring.
In order to continue their quest towards a complete periodic table, scientists couldn't just continue isolating elements from existing materials. They had to create them.
So we use what's called a particle accelerator, or specifically a cyclotron, which is a large instrument that accelerates ions to a fraction of the speed of light.
Cyclotrons have been used to discover heavy elements ranging from curium to plutonium. And most recently, Dr. Shaughnessy's team collaborated with a lab in Russia to complete the periodic table's 7th row, the home of the superheavies.
When we make one of these new elements in the cyclotron, we really have to just add up protons. So for instance, if we wanted to look for element 116, we could take something with 20 protons, and we can take something with 96 protons. And if we can get those two nuclei to completely fuse together for even a short time, that means we have an element 116, one atom of it. These elements are very short-lived. They're not very stable, so they decay very quickly.
Some superheavy elements only exist for just milliseconds. So in order to confirm they created one, the team had to work backwards, sifting through the data to find the signal that told them a heavy element was actually there.
The Flare-Off lab in Dubna has an incredible cyclotron that's really a workhorse. And we at Livermore have access to various target materials. So we provided our expertise, the Russians provided their expertise, and together discovered elements 114 through 118.
While efforts to discover more elements continue, Dr. Shaughnessy and Dr. Gates have shifted their sights to studying the ones we already have. We know almost nothing about these super heavies, including whether or not we've actually put them in the right place on the periodic table.
Right now, when an element is discovered, we're putting it in the periodic table based on its number, mostly for convenience. But the periodic table, let's remember, was constructed to be a living document on the chemistry of these elements.
So the models predict that these heavy elements might behave unexpectedly due to something called relativistic effects.
We have these big, massive nuclei, and what's happening is they're accelerating their electrons to near relativistic speed. They're going so fast that they're being dominated by the theory of relativity. And what that does is it's changing the mass of the electron, and that's changing how it bonds and its chemistry. So when we get to this last row of the periodic table, what we see sometimes is that the chemical properties down a given group may invert or do something totally different.
We believe that we have them in the right position, but we also don't think we've proven that. And so what we did was we built Fiona to actually prove that what we think is true actually is true.
Hooked up to the Lawrence Berkeley National Lab's 88-inch cyclotron, Fiona is one of the newest tools designed to study superheavy elements. Its primary goal is to experimentally confirm their mass numbers. But before Fiona can measure the mass, the team needs to create a superheavy element.
So we are in Cave 1 at the Building 88 facility. The beam comes from the cyclotron, which is right through that wall. And then it travels all the way down this line here until it reaches our target on the other side. This is what our targets look like, or this is 3/4 of a target. We have just a couple thousand atoms thick of whatever our target material actually is. What we're interested in is one nucleus from the beam hitting one nucleus from the target and completely fusing. The problem is that doesn't happen very often. Nuclei are very small compared to atoms. So a nucleus is about 10,000 times smaller than the atom itself. So when the beam comes in, what it actually sees is mostly empty space. So it actually passes through our target, mostly. And then very, very rarely, we'll get this head-on collision that makes that atom that we want. Right inside this box, that's where our elements are made. Now our job is to find a way to separate all that junk that we don't want from that one atom that we do.
Everything travels through the Berkeley gas-filled separator, a machine equipped with giant magnets that bend the excess atoms away from the superheavy the team is interested in. Then it enters stage 1 of Fiona.
That's all of that equipment over there. It traps it in a small volume, and then it sends it on to stage 2 of Fiona.
Magnetic fields then send the super heavy atom into a specialized loop. And it's the specific path it takes within that loop that tells the team its mass.
Fiona's first scientific experiment started in June of last year. We were able to confirm that those new heavy elements that we've discovered really do have the number of neutrons and protons that we think that they do.
But confirming that isn't quite enough to know for sure that we've put them in the correct place on the table. We also have to explore their chemistries.
We have atoms trapped in a cubic millimeter of volume for a time that we pick. We can add in different gases, and we can change the amount of time we trap things for. We can look, does this gas react with this atom? And if so, what does it make? We can actually learn quite a bit about the chemistry of these new elements.
And at Dr. Shaughnessy's lab, her team is looking into alternative methods.
Here at Livermore, we're trying to develop a way to do aqueous chemistry of 114. So hopefully this collection of data from both the gas and aqueous phase will start to paint a more complete picture. If we do see some real shift in chemistry, we would have to rethink that last row. What does that mean for our periodic table?
150 years after its conception, the periodic table is reaching a turning point. As Dr. Gates, Dr. Shaughnessy, and teams around the world continue to unlock the mysteries at its borders, they're also starting to question just how much further those borders can be pushed.
There are people who have tried to predict where the periodic table will end. The most common number thrown about is around element 172 or 173.
The issue is that the probability of making the two nuclei come together, it gets smaller and smaller as we go up in element numbers. So with element 118, it was a very small probability that we would make it. Now for 119 and 120, it's even getting lower and lower. In order to push out to heavier elements, there's going to have to be some real shifts in technology compared to what we have now.
You're trying to answer a basic scientific question. How many elements are there in the universe, and what are their chemical properties? And that's something that's interesting regardless of whether or not there's any scientific applications for it.
If you break down an advanced piece of technology, a new medicine, or an energy source to its essential parts, you always end up with the same thing. Those same blocks that make up you and me and the stars in the night sky. It's about the elements themselves.
The formation of these elements alone tells us a lot about nuclear theory and how the nucleus holds together. We've already changed over the decades how we think of the nucleus. So that's where the application is right now, is really in just our fundamental understanding of the universe.
The truly periodic table. The periodic table is this chart with a strange shape, with letters and numbers, neither a square nor a rectangle, with such a characteristic shape. Unmistakable. Some people know what each of these letters represent. C is the chemical symbol for carbon. O is the chemical symbol for oxygen. The chemical symbol for iron is Fe. Zn is zinc. There are even those who know the chemical symbol for sodium is Na, because it comes from the Latin natrium. Or that the chemical symbol for gold is Au, because in Latin it was called aurus. And also some know the meaning of the numbers that appear next to the letters, like for example the atomic number, which is the number of positive and negative charges of the atom. But what exactly is the periodic table? The periodic table is a chart that represents all 118 chemical elements that constitute the known universe. Everything around us is made up of at least one of these elements. 94 of these elements can be found in nature, and the rest were obtained in laboratories. 118 elements may seem too little for an entire universe, but it's not. Let's see. In stars like the Sun, 94% of all the atoms are hydrogen.
The human body itself is very scarce on chemical elements. For every 100 kilos of weight, 65 kilos are oxygen atoms, 18 kilos are carbon atoms, and 10 kilos are hydrogen atoms, which leaves little room for all the other essential elements. Nitrogen, calcium, phosphorus, potassium, sulfur, chlorine, sodium, magnesium, iron, cobalt, copper, zinc, iodine, selenium, fluorine. The wonder of the chemical elements is that they combine with each other, and there's an almost infinite number of possible combinations that produce all the different chemical compounds needed to keep us alive and build everything around us. The water we drink, obtained by combining an oxygen atom and 2 hydrogen atoms. The glass we drink it from. The sugar in our coffee. The coffee. The cup and the metal of the little spoon we stir it with. The plastic our computer is made of. The rubber on the tires of our car and the gasoline that makes it run. Proteins. DNA. Everything around us and inside us are atoms that combined. An atom is the smallest recognized division of a chemical element and consists of a central core, with protons, positive charge, and neutrons, no charge. Surrounded by a cloud of electrons, negative charge. The properties of each chemical element are defined by the atom's nucleus and by the way electrons distribute in layers around it. These properties define the way atoms combine, or not really. Atoms react with each other through electrons of the last layer, the outermost layer. If the last layer has the same number of electrons, this means that the properties of these atoms are identical. The distribution of the elements in the lines and columns of the periodic table is not random, or just a question of design. The position of an element on the table tells us something about its chemical and material properties, and helps us to know and predict how 2 elements can combine. The periodic table organizes the elements from smallest to largest, according to its core and the distribution of electrons. In the first column of the table, we have the elements that have a single electron in the outer layer. And in the last column, we have those who have filled this layer. That's why each chemical element in the periodic table has a very well-defined neighborhood. Above and below it has elements with the same distribution of electrons and very similar properties. And on its right, it has an element that has an electron and 1 proton more, and therefore has different properties. We call it periodic because in this table, the elements become similar again periodically. Let's see, if we start at 3, lithium, the properties will vary regularly along the line until 10, neon. Here, the last layer of electrons gets full, and we move on to the next line and back to the first column. The properties of this element, 11, sodium, are again identical to the element that is directly above it, and so on. The tricky part is that the number of electrons filling one layer varies, and their distribution follows well-defined rules of quantum chemistry. 2 in the first, 8 in the second, 18 in the third, but in 2 phases. Which makes it necessary to distribute the chemical elements in the table in such a weird way. But in the end, everything makes sense, and we have the whole universe in a single table.
I mean, the one thing I can say is it pays to be naive. If I had understood the magnitude of what I'd taken on, I might never have done it. Sometimes you're so close to it that you don't realize what a massive thing it is. When you have time to step back, you think, wow, did we do that?
The year 2012 brought the science discovery of the century, at least so far. A team of physicists may have found the missing link in our picture of the universe, the Higgs boson. It happened here, outside Geneva, at the laboratory known as CERN.
We knew right at the start that this was going to be a difficult endeavor. It was quite ambitious because some of the instruments that we needed to clearly see these things didn't exist at the time.
The Large Hadron Collider is the world's biggest and most expensive experiment. It was designed to whirl beams of subatomic particles around a 17-mile racetrack and smash them together at the speed of light.
To see the Large Hadron Collider come from a 16-page report to a machine which costs tens of billions of dollars, obviously it means a lot of work.
Think of building an apartment building where everything is known to a couple thousandths of an inch. That's not so easy.
They built 2 detectors, each 7 stories tall, to record the collisions. The detectors were capable of taking 40 million pictures per second.
And the first time we collided, no one had ever seen this before, except in simulations. It was like fireworks. It was, the whole screen lit up.
The amount of data generated was massive. Armies of scientists were needed to analyze it.
Discovery is not like a eureka event. It's statistical discovery. So it's very, very difficult, for someone to say, I've got it. They have to go through, it's like finding a needle in a haystack.
We're looking in hundreds of billions of collisions, and indeed in total now we've collected about, if I get the numbers right, about 250,000,000 proton-proton collisions have been observed in order to see the handful of Higgs candidates that we see.
The elusive Higgs particle. It gives mass to other elementary particles. Without it, there would be no atoms, no stars, no life as we know it.
All the other particles carry forces. So all these particles are all worker bees, The Higgs is sort of like the mother of everything.
For nearly 50 years, it was just a theory, until the morning of July 4th, 2012. Scientists around the world gathered to hear the announcement.
Today is also a special day because we hear 2 presentations from the 2 experiments, Atlas and CMS, on their update on a search for a certain particle.
I was very tired, of course, and you need a lot of energy to give this kind of talks in emotional energy and emotional, very solid nerves.
Pleased to present here today.
There was a lot of adrenaline. And I remember at one point holding the wand up with the laser and pointing at the screen. It was really quite shaken. And I said, I must be nervous.
In some sense, we were so much focused in preparing the results that I had not realized until I was actually here how big what we were announcing was and how big an event it was.
And we conclude by saying that we have observed a new boson with a mass of 125.3 plus or minus 0.6 GeV at 4.9 standard deviations.
And the applause was so long. It was endless.
In the audience was Peter Higgs. He was one of the men who had first predicted the existence of this particle all the way back in 1964.
July the 4th is really a fantastic example of the power of pure reason, the power of mathematics back in 1964, combined with the physics and engineering prowess.
Mankind has this wish, has always had this wish to understand the world around them. It's curiosity that's driving us, that in order to understand really how the universe is put together and what the fundamental structure of the universe is. Finding this new particle really takes us a step forward.
It's certainly the biggest discovery of the 21st century. The 21st century is young, so let's hope that there will be many more.
Can you grab my bag too, Andre?
Today, we are starting in the non-alphabetical order, and I ask Joe Incandela from CMS to take the floor. Okay?
It took quite a bit of effort to compress all the work of really thousands of people over many years into the small number, I think 175 slides, that I show here.
This has been such an intense adventure. This is why we're all here. This is one of the reasons, I should say, but one of the main reasons. The specifications for the detector were based on what we would need to discover a standard model Higgs.
If we combine the ZZ and gamma gamma, this is what we get. They line up extremely well, and in the region of 125 GeV, they combine to give us a combined significance of 5 standard deviations.
Although our life will not change the day after the discovery of the Higgs boson, a step forward in fundamental knowledge is always a step forward for mankind, and sooner or later it brings to progress.
This distribution is extremely clean, except one big spike here, in this region here. So, zooming in this region.
It's a very fundamental question, which is also relevant to, to the universe and our world, also our day-by-day life is. It's not really something abstract enough.
So just to be clear, we've definitely found a new particle.
Yes.
It bears a resemblance to the Higgs boson. Is it the Higgs boson?
It could be a Higgs boson. It's just the beginning. When you just reach the point where you can say something's there, you rarely have enough data to give any details about what its characteristics are. On the other hand, everything we know about it right now is consistent with the standard model Higgs.
I think that you have built the most incredible scientific instruments, from all the way from the hardware to the data analysis, in global collaboration, and I think you should all be very proud. Thank you. I went into that seminar expecting a good result, but to see 5 sigma up there on both detectors was a total surprise to me. I was gobsmacked, as they say. You must understand, these machines are not easy. The background is enormous. Getting the signals out is incredibly difficult. And one after the other, Atlas and CMS showed us what a fantastic job they've done.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime. It's taken...
Probably the largest scientific instrument that's ever been created.
At the CERN lab in Switzerland, huge tools are needed to detect tiny particles.
But the real action happens underground in a cavern attached to this 17-mile circumference ring. 3,000 physicists working on this huge detector. This detector is 80 feet tall, 140 feet long. So imagine that.
With support from the National Science Foundation, physicists Michael Tutz at Columbia and Kyle Cranmer at New York University are among the 21st century explorers who have been searching for the mysterious Higgs boson. It's a subatomic particle that gives other particles, like quarks and electrons, mass. So tiny, yet where would we be without it?
The universe would be a fundamentally different place. There'd be no life, there'd be no stars.
Inside the world's biggest atom smasher, the Atlas detector works like a huge digital camera. It records the collisions of hundreds of billions of protons at nearly the speed of light.
Our digital camera takes 40 million pictures per second.
Thousands of computers, like these at New York's Brookhaven National Lab, filter the images of those collisions, looking for traces of the Higgs boson, which decays quickly.
And the trick is not so much throwing stuff away, but making sure that you don't throw away the good stuff.
In July 2012, scientists celebrated.
We have discovered a new particle, a boson.
We've seen something, and that something looks like a Higgs boson.
Now that we have this new particle, we need to study it like crazy. We need to measure all of its properties.
The elusive Higgs, also known as the God particle, has captured the imagination of non-scientists too. It even has its own music videos.
This is a triumph of human curiosity. It's really key to our understanding of the universe.
Tutz and Cranmer say that at CERN, the Higgs is only the beginning. More exotic mysteries lie ahead, from figuring out what happened after the Big Bang to discovering extra dimensions of time and space. For Science Nation, I'm Miles O'Brien.
It all started in 1964, when a young English physicist named Peter Higgs suggested something about space that was so radical, it nearly ruined him.
I was told that I was talking nonsense, that I couldn't be right. So they clearly hadn't understood what I was saying.
Higgs and a few others were wrestling with a puzzle which comes down to this. The fundamental particles in the universe all contain different amounts of mass, which we usually think of as weight. Without mass, these particles would never combine to form the familiar atoms that make up all the stuff we see in the world around us. But what creates mass? And why do different particles have different masses? Try as they might, no one had been able to answer this perplexing question. Then, one weekend, after a walk outside Edinburgh, Higgs had a peculiar idea. Using mathematics, he imagined space in a new way, as something like an ocean. Particles are immersed in this ocean and gain mass as they move through it. To see how this works, think of a particle's mass like an actor's fame. And the Higgs ocean is like the paparazzi. Some particles, like unknown actors, pass through with ease. The paparazzi simply aren't interested in them. But other particles, like superstars, have to push and press. And the more those particles struggle to get through, the more they interact with the ocean and the more mass they gain. Higgs was convinced he'd made a great discovery. But when he submitted his idea to a journal at CERN, it was rejected. Undaunted, Higgs honed his theory further, until he was offered the chance to present it at Einstein's old haunt, the Institute for Advanced Study in Princeton. There, he expected his new idea would meet some of its toughest critics.
I was happily driving up the freeway, and then there was a sign to turn off for Princeton, and that really confronted me with what I was going into. I broke out in a cold sweat and started trembling, and I had to pull off the road to recover.
But Higgs persevered. It was the first in a series of talks that would convince colleagues far and wide that he was onto something profound.
Eventually, I sort of wore them down. I felt I'd sort of triumphed. So I enjoyed the parties which followed.
Today, the idea Higgs pioneered, called the Higgs field, is crucial to our understanding of space.
The Higgs field is everywhere. It's something that even in the emptiest vacuum of space has an effect. It gives you mass. So I think Higgs actually deserves credit for being one of the people that said space is stuff. It has properties in it that are intrinsic, that you can't get rid of, you can't turn them off.
The only problem? There's no physical proof that the Higgs field exists. At least not yet. But here at CERN, scientists are attempting to smash particles together with so much energy that they will knock loose a piece of the Higgs field, producing a tiny particle of its own. It's as if they're trying to chip off a piece of space.
We think that if we knock into space hard enough with particle accelerator collisions, that we can actually make a Higgs particle come out of empty space.
Our whole understanding of matter as we now have it would just fall apart if the Higgs field didn't exist.
I don't think anybody seriously doubts that we will see it. Certainly if we don't, that would be an extremely bizarre outcome.
Finding the Higgs particle would be a major milestone, establishing that the emptiest of empty space has an impact on all of matter.
The Higgs is part of what has been termed as the Higgs boson.
Right.
So explain the Higgs and the boson both.
Okay, we're celebrating the fact that we have found a new particle never seen before in Mother Nature by slamming two beams of proton at trillions of electron volts. And this particle, we think, was in fact, a particle like this was the fuse that set off the explosion which created the universe. So that everything we see around us, the galaxies, the planets, the Earth, life itself, is a byproduct of an explosion which was set off by a Higgs-like particle. We think that originally the universe was a gas of particles with no mass at all. Think of a crystal, beautiful crystal, totally symmetrical, but useless. It exploded. And the shattering of this crystal gave us all the masses of the particles today. The electron, the proton, the neutron, the atom. Why do we have a nucleus? Why do we have a proton? Because they have masses. So the explosion of the particle broke the original perfect symmetry of this crystal, giving us the broken world we see today of planets, stars, galaxies, you, me, even love. All of it from this explosion triggered by a Higgs-like particle.
Okay, it's still very complex, but I know that you often break out into the sociological implications of science as well. This is the beginning of a very, very big conversation, isn't it? This isn't just science. This is how science may actually disprove religion, because you said you cringe when you hear God particle. Is that where we may be headed with this?
Even more than that. Realize that the Higgs boson takes us to the instant of creation itself, and we can run the videotape before the Big Bang. We can talk about the universe before the creation of the universe itself. If our universe is a soap bubble of some sort and it's expanding, there could be other soap bubbles out there, other universes. And so this is where the next step beyond the Large Hadron Collider comes in. We're going to look for evidences of a pre-Big Bang universe, perhaps the existence of other universes. And then, of course, we have the question that everyone asks me, is Elvis Presley still alive in another parallel universe?
Is he?
Maybe. You can't rule it out.
Come on, we're going there? Really?
We're going into areas that take us before the instant of Genesis chapter 1, verse 1. We're talking about going before the beginning itself. I tell you, this is deep. This is really deep. It has philosophical, theological implications as we talk about a universe, a parallel universe, other universes out there coexisting with ours. And the Large Hadron Collider, this gigantic machine in Geneva, is the key to perhaps proving the existence of these other dimensions.
After nearly 50 years of research and billions of dollars spent, two scientists have now been awarded the Nobel Prize for predicting the existence of a particle that holds all matter in the universe, including us, together. It is the biggest physics breakthrough in decades. But as Stuart Greer reports, one of the scientists behind it is staying humble.
This year's prize is about something very small that makes all the difference.
After discovering something so momentous it's known as the God particle, there was little surprise when the Royal Swedish Academy of Science bestowed this year's Nobel Prize for Physics to Belgian scientists François Englert and Peter Higgs of Britain.
For the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass.
In 1964, both men theorized the existence of a strange and elusive particle that gives weightless atoms their mass, thus explaining why all matter in the universe, including us, exists. But it wasn't until last year that their bold theory was confirmed by scientists at the world's largest atom smasher on the French-Swiss border.
I think we have it.
The discovery could explain deeper mysteries, like what is dark matter that makes up 99% of the universe. The scientists will split a $1.25 million award. Englert learned of the honor over speakerphone.
Well, thank you very much. I feel very well, of course.
But the 84-year-old Higgs, who is famously shy, was nowhere to be found. He went on holiday without a phone to purposely avoid the limelight. But he left this message in case he won. I am overwhelmed to receive this award. I hope this recognition of fundamental science will help raise awareness of the value of blue sky research. In a rare appearance last year, Higgs couldn't hide his emotions on news that his theory, once dismissed by astrophysicist Stephen Hawking, was indeed correct.
For me, it's really an incredible thing that it's happened in my lifetime.
Now add to that a Nobel Prize for the humble Higgs, who today proved even more elusive than the mysterious particle he discovered. Stuart Greer, Global News, London.
Geneva, Switzerland. Here, buried over 300 feet beneath the Earth and covering a remarkable 17-mile expanse, is the largest and most complex machine ever created, the Large Hadron Collider, or LHC, smashing tiny protons together at speeds of nearly 670 million miles per hour. The LHC creates such intense energy that some people are afraid it could actually create a black hole and swallow up the entire Earth.
The Large Hadron Collider is a real triumph of human civilization. It's easily the most complicated and powerful device that the human beings have ever built. You're actually firing two protons into each other and having them collide with an enormous release of energy, recreating conditions in a very small area similar to the Big Bang in its very earliest instant.
It is a bit like going back in time towards the Big Bang or the beginning of the universe, getting to points in the history of the universe where the energies were that high.
On July 4th, 2012, thousands crowded outside an auditorium at the European Organization for Nuclear Research, or CERN, to hear the announcement of the LHC's first major finding. Streaming the event live across the world, scientists prepared to reveal a discovery that could solve a decades-old mystery about the nature of our universe.
The atmosphere in the room was incredible. It was not like a normal physics symposium or seminar. It was truly something of completely different magnitude was going to be announced. That it is completely extraordinary, which it was.
What the scientists at CERN had discovered was a tiny bit of matter that some call the God particle.
Scientists around the world celebrated the discovery of the God particle as a milestone in human knowledge and thought that it's going to open up new layers of our understanding of reality.
But just what is the so-called God particle? And what is it telling us about the universe? Known in the scientific community as the Higgs boson, the particle was first theorized by physicist Peter Higgs in 1964. Its discovery confirms the existence of an invisible force throughout the universe, known as the Higgs field. Scientists believe when particles interact with this field, they acquire mass, which slows them down and allows them to form matter, such as planets and stars.
There's great excitement in the scientific community because the Higgs field permeates all of space-time. It's possible, theoretically, to effectively switch off the mass of particles and achieve near light speed very easily. This could open up not only the planets, but the stars to human exploration.
Whether it's through science, religion, philosophy, or the ancient astronaut theory, the fact is we are all seeking answers to the same questions. Who are we? Where did we come from? And ultimately, where are we going? And so we celebrate a discovery like the Higgs boson or God particle because it brings us that much closer to answering the questions that have fascinated humanity for thousands of years.
July 4th, 2012, and scientists from CERN, the European Agency for Nuclear Research, step in front of hordes of journalists to unveil a scientific discovery that signals a new dawn in understanding our universe.
It is a milestone. I think we can all be proud.
Researchers created what's been called humanity's largest and most complex scientific experiment. A 27-kilometer, one-of-a-kind machine buried some 175 meters below ground to discover the Higgs boson, a pivotal building block of our universe.
So the Higgs boson is a fascinating particle because it's the simplest one. This has completely changed our vision of also the universe, because corroborating the fact that there's a Higgs boson means that we live in a vacuum that is very special. So it has changed a lot on the way we think about our universe in general.
The boson is part of what physicists call the Standard Model, a way of explaining what for 13.8 billion years has held particles together, maintaining our universe. There's just one problem. No scientists had ever detected it. That's where the Large Hadron Collider comes in.
So we're accelerating protons in opposite directions to very high energies in a 27-kilometer long tunnel, and then we bring them to collisions in different interaction points where we have done experiments, essentially recording the data.
Okay, Olivier, why don't you tell me what's happening here?
What we see here is an event display, which essentially is a recording of one of our proton-proton collisions. If you like, it's a three-dimensional imaging of the data we are taking in our experiment and then being displayed in this way.
Mm-hmm.
So it's one out of billions of collisions we are taking.
So this is like real-time imagery of what you're trying to do here. Teams like Oliver's from Geneva to Chicago analyzed the debris of millions of collisions. Collisions, they say, recreate the beginnings of the universe. What are you hoping to achieve here?
Well, these collisions essentially are at very high energy, at the highest possible energy mankind has generated in particle physics collisions so far, and we hope to achieve conditions which must have existed very close to the beginning of our universe, namely after the Big Bang.
Of course, recreating the Big Bang is not a matter of just flipping on a switch. The LHC is managed by a control center on the French side of the border, where engineers like Mirko are responsible for injecting some 7 tera-electron volts into magnets, accelerating protons close to the speed of light.
On this screen, on this chart, you see the past 24 hours at the LHC. You see the black line indicates the energy of the machine, and the blue and red lines indicate the intensity of beams that are injected in the two directions into the LHC. We actually put them into collisions where the experiments can turn on their detectors and start collecting data.
If something was wrong with the machine, what would this chart look like?
Something like that, for example.
Is that telling me something's wrong?
Yes,
okay.
Indeed. We decided to extract the beam, restarting from zero, and it went smoothly up and this time, and it was pretty fine.
And while the machine runs smoothly now, that wasn't always the case. In 2008, after a decade-long construction, disaster struck when a short circuit caused an explosion that rendered the machine inoperable. Tell me about the worst day ever in this command center. What happened that day?
2008, when we broke the machine just 9 days after switching it for the first time.
You broke the machine?
Yes. Yes, we got a technical problem into the ring, and there was one of the sectors that experienced an electric short, and actually there was somehow a small explosion inside the magnets. That was the worst day of my life. Everything got red on the screens.
The team almost halved the energy used by the system for the following years, so when they discovered the Higgs, everyone was a little shocked.
So there's a period of disbelief. Of course, as an experimental physicist, then when you're through observing something new, you just try to make sure that you're not observing something fake. When we finally accepted that it was there and we started to study it, so it was an incredibly exciting period.
But the Higgs discovery also reveals how much we still don't understand.
Now we really want to go beyond that model, because we know that it does not explain everything we see in our universe. As a matter of fact, it only explains 4% of the matter which we have in our universe. So there's much missing. And with the next phase of the LHC, we are now hoping to make new discoveries which go beyond our present understanding.
In June 2015, the system was turned back on after a significant upgrade, and this time delivering twice the energy used during the Higgs discovery. The scientists say they could be on the path to discover the gravitational forces that hold our galaxy in place, and even, potentially, miniature black holes.
There is theories out there which suggest that these microscopic black holes could be produced in high energetic proton-proton collisions. And if we indeed find first signs of these microscopic black holes, then this could open the path to new extra dimensions in our universe.
But for the team that first discovered the Higgs, now it's not just what they think they might find, but what they've never seen coming.
I would say I have two dreams. One of course, is to see something completely unexpected. And of course, there's also maybe another aspect. There are fundamental theories that are incredibly elegant, incredibly beautiful, on how they explain a lot of the mysteries that we have in our fundamental laws of physics.
A scientific discovery this evening. It is making huge headlines across the globe, something truly historic. Researchers tonight say they think they have finally discovered the so-called God particle, the Higgs boson particle, after the scientists who helped begin the search decades ago. But tonight here we ask, is this the bang in the Big Bang Theory? And we get help from Dr. Michio Kaku breaking it down.
There were cheers and thunderous ovations after a moment scientists had longed for. Tonight they believe what's popularly known in the science world as the God particle has been discovered. The particle that could unlock the key to what gives all matter in the universe its size, its shape. Just like gravity, scientists long knew it was there, then Isaac Newton actually discovered it. And now, after decades of knowing this particle exists, they have finally seen clear evidence of it. They discovered it while smashing atoms together, breaking them down. And right there in the energy released, the newly discovered particle.
You've been smashing these particles together, trying to break it down and find it?
That's right. We have this machine which accelerates protons in two different directions. They slam together, creating 14 trillion electron volts, temperatures and energies not seen since the instant of the Big Bang. When these two beams of protons collided, a fantastic energy, a spray of subatomic particles. Then we run the videotape backwards. We run it backwards to find what particle existed at the very instant of the collision.
And this particle was right there.
Was right there.
So when we hear Big Bang Theory, this would be the particle at the heart of it all.
That's right. The Big Bang Theory simply says the universe expanded 13.7 billion years ago. But what put the bang in the Big Bang? Why did it bang? What is the energy that drives the Big Bang? The Higgs particle could have the key to this whole cosmic puzzle.
So you should be at some party right now.
Yeah, that's right. I'm late for a party.
Well, it is a massive day in science as scientists at CERN have announced they believe they've discovered the Higgs boson, the so-called God particle that gives matter its mass. But how exactly does that work? Well, we have Martin Archer, physicist at Imperial College, to help explain. So how does matter get its mass from the Higgs boson?
Well, so the idea is that the Higgs boson forms this Higgs field. So you have these particles popping in and out of existence everywhere through the universe, just like here. But to explain the actual mechanism that gives mass, it's best to use an analogy. So if we say that these particles are actually teenage girls, and therefore mass is something to do with, like, fame. So we've got Justin Bieber, we'll get onto him in a bit. But if we were to just take just an average person, then if he moves through this Higgs field, the teenage girls aren't going to care.
They don't
about
know who he is.
Exactly. So he's going to go through completely unimpeded by all the teenage girls that are dotted everywhere. Justin Bieber is a completely different case, though. He goes along and all these teenage girls flock around him, and obviously if you've got loads of people around you, you can't move as fast as you could otherwise, so he gets slowed down by the teenage girls, and therefore he has this sense of mass, this drag, this inertia, and that's basically how the Higgs mechanism works. And today we think we have found these teenage girls, or the Higgs boson particle.
And the more of these particles, the more massive it is, essentially. The bigger the star, basically, going
the more they're
through this field.
attracted, the more he's going to get slowed down, and therefore he's more massive.
Fantastic. Well, thank you so much for that explanation. Still a lot more questions to be answered, but at least the Higgs boson finally seems to have been identified.
Scientists who solved a mystery of the universe were awarded the Nobel Prize in Physics today. Peter Higgs of Britain and Francois Englert of Belgium suggested that a subatomic particle known as the Higgs boson gives mass or substance to everything we know. Mark Phillips tells us more about what many call the God particle.
They've sung his name, and they've smashed subatomic particles against each other to prove the Higgs boson particle that he theorized 50 years ago must exist actually does. And now in Stockholm, they've given the biggest prize in science to the man who gave the particle its name.
Professor Peter Higgs at University of Edinburgh, United Kingdom.
Peter Higgs did show up in July last year when scientists at Europe's atom-smashing Large Hadron Collider outside Geneva confirmed his long-held theory that there was a so-called God particle that explained why the universe held together.
For me, it's really an incredible thing that it's happened in my lifetime.
The theory is that the Higgs boson particle acts as a kind of nuclear glue that allows the stars, the planets, and everything else, including us, to exist. It took the 17 miles of tunnel and $10 billion of investment in the world's biggest collider to prove it. But on the day of his Nobel triumph, Higgs, a private man, was as elusive as the particle that took so long to find. Higgs wasn't to be seen today. This is him working at the University of Edinburgh earlier this year. Higgs's co-winner, the Belgian physicist Francois Englert, who worked on the same problem in the 60s, was less elusive. He said he was happy. The staff at the Collider, too, were celebrating the award. And now the choir of workers there has something else to sing about. Mark Phillips, CBS News, London.
It's a discovery big chunks of the scientific world had been waiting for, finding a new subatomic particle that could bring fresh understanding to how the universe works. The announcement brought applause and cheers and standing ovations and a special hand for Peter Higgs, the Scottish physicist who predicted the existence of such a particle back in the 1960s.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime.
But those at the world's biggest atom smasher who've been heading up the hunt for the Higgs boson, seen as the key to understanding why matter has mass, are still unwilling to say for certain that is what they've seen.
As a layman, I would say we have it. But as a scientist, I have to say, what do we have?
But word that two independent teams at the Large Hadron Collider, who are studying high-energy collisions of protons, have observed the particle, which has behaved a bit differently than predicted, generating big excitement in those who follow the investigation of dark matter, antimatter, and the Big Bang, the massive explosion where many theorize the universe was born.
The studies that are going to be done by the LHC over the next months and years, they will tell us more about the physics of the universe in the first microsecond of its creation.
Scientists at the Collider on the Swiss-French border and elsewhere will now pounce on the findings to see what they mean for their theories and whether this opens the door to a new kind of physics. In the meantime, though, one thing seems certain: a lot more atoms will get smashed in the process. Karen Sloan, The Associated Press.
It's not often a scientific breakthrough gets sung about. But the workers at the world's largest atom smasher are singing about the Higgs boson particle, the so-called God particle that's been the holy grail in the world of physics for almost 50 years. Ever since Peter Higgs, now 83, theorized that the particle must exist in order for the universe and everything in it to hold together, to have what the physicists call mass. Without Higgs boson, there would be no stars, no planets, no us. So at the Large Hadron Collider on the French-Swiss border, they've been blasting bits of atoms at each other and measuring the even tinier bits the collisions produce.
As a layman, I would now say, I think we have it.
Rolf Hoyer, the project's director, announced the results to an appreciative audience of scientists. Though they couldn't say they'd positively found the Higgs boson particle itself, they could say they found one that walks and talks like one, and maybe it. Peter Higgs himself looked satisfied, his theory vindicated.
For me, it's really an incredible thing that it's happened in my lifetime.
The challenge now is to explain what it means. Professor Heinz Wolff has been trying to explain science for decades. He even devised a machine to blast meat pies at each other to demonstrate what an atom smasher does. So what does the discovery mean for us?
If you're the lady in the supermarket, it isn't going to make any difference to you. It's really a big cultural step.
Other than that, the supermarket wouldn't be there unless this...
or wait the supermarket, or mass the supermarket.
The supermarket exists, and the universe exists. And now these people believe they found the tiny particle that provides the cosmic glue that holds it all together. Mark Phillips, CBS News, London.
As a layman, I would now say, I think we have it. You agree?
Until today, the so-called God particle, the key to our understanding of the universe, existed only in theory, but not anymore. Collecting data like this, scientists at CERN have announced the discovery with 99.999% certainty that the Higgs boson does exist, the so-called God particle. Professor Peter Higgs, now 83 years old, who first theorized its existence in 1964, was in the audience for this historic moment.
For me, it's really an incredible thing that it's happened in my lifetime.
So what is the God particle, and just what does it do? Well, in one sense, it is the missing link to this massive equation. This is the standard model for particle physics, and this is our understanding of how the universe works. The Higgs boson gives us mass, which is how we measure matter, the stuff we are made of. Scientists say without mass, stars, galaxies, and planets would not have been able to spin themselves into existence after the Big Bang. So how did scientists find it? Well, with a massive particle collider at CERN, 27 kilometers of tunnels under Switzerland and France. Researchers smashed particle beams together to see what's inside, effectively recreating the Big Bang trillions of times over and over. And this is what they saw. Subatomic debris, including the decayed remains of what they say appears to be the Higgs boson, thereby proving its existence. But the mysteries of the universe are not solved yet. Consider this. All those galaxies, planets, and stars, everything we can see, well, they make up only 4% of the universe. There's still a lot more to discover. Finding the Higgs boson, the God particle, just opens another door.
Following weeks of excitement, the results are out. Scientists at Switzerland's CERN Research Centre say they've detected signs of the missing link in particle physics, but there's no outright discovery. Scientists have been trying to recreate conditions in the first trillionth of a second after the Big Bang, the creation of our universe. Two separate experiments at the Large Hadron Collider have involved firing protons into each other inside a 27-kilometre-long tunnel. The teams have analysed the debris from those collisions, trying to locate the so-called God particle. Scientists believe that after the Big Bang, a force known as the Higgs field formed, together with its associated Higgs boson, a subatomic particle. This field is thought to be the reason other particles, and therefore all objects in the universe, have mass. Without it, we'd all be rushing around the cosmos at the speed of light.
This is about amassing knowledge about the origin of mass and the origin of the universe. It's about understanding how the particles that we know are made of, how they get mass and where they come from.
The two CERN teams will continue searching for the Higgs boson, but for now they're reporting signals of the boson in the same mass range. So while it's too early to say with certainty that the God particle does exist, it's got the science world buzzing. Nadeem Barber, Al Jazeera.
When the discovery broke in Geneva, scientists around the world stood and cheered, including a team of about 40 scientists out of the University of Florida.
It's very emotional. Remember, this is the biggest thing that's come out of the field in I don't know how many years, probably since the 1960s.
Professors Paul Avery and Konstantin Matchev were among those key to the discovery of the Higgs boson particle, found by essentially recording the collision of protons in a giant superconducting supercollider.
When these two beams of protons collided at fantastic energy, a spray of subatomic particles. Then we run the videotape backwards. We run it backwards to find what particle existed at the very instant of the collision.
The so-called God particle may provide proof for the Big Bang theory of creation and explain why we can actually see and touch matter in the world.
And that's a new force of nature. And whether and when we're going to be able to tame that force and put it to work, I don't know. It may take years, it may take centuries, but it's a very fundamental discovery.
UF expects a surge in enrollment by students anxious to be on the leading edge of discovery. The finding puts the school on the map for something other than sports.
It's nice to see people cheering for a physics result, not just at a football rally.
And though other universities contributed to this week's discovery, there's more than a particle of pride in Gainesville.
Go Gators! A Gator chomp, right?
If this exists, as we seem to be getting closer to understanding it does, what would that do? What would that mean?
It may mean we'd be able to unlock limitless energy. Let me just put it that way. It may be that we would understand the next secret of the universe, that we would know, we'd be another step closer to knowing where we came from. We'd be another step closer to understanding the universe itself, which is ultimately quite a mystery to us.
What is this Higgs boson God particle?
At the very, very beginning of the universe. See, people here, as a matter of fact, I'm in Los Angeles. People at Mount Wilson, not far from here, notably Edwin Hubble, noticed that all the stars, everything's moving apart. So he reasoned that everything was all together at one time, and this would be the Big Bang. Well, at that time, it is speculated by mathematical, elegant physical reasoning that everything was kind of one thing. But then after the Big Bang, things started to separate. Things started to take on different properties. So that pure energy, like light, has no mass. The particles of light have no mass. The particles that make up you and me, like you've probably heard of protons and neutrons and electrons, they have mass. And do you know why?
No.
No one really is sure why. But it could very well be that there's an exchange of particles. Nowadays, we view these things as particles. We do experiments to detect particles, and you detect particles. Protons are made of quarks, which are held together with gluons. No kidding. And so it could be, it's very reasonable that these other particles all exist in this ether that would be called, named after Peter Higgs.
Right.
That is then infused with little particles that give them mass, that help them have mass. And this would be the Higgs boson.
I'm sitting in the control room of the GSI Institute, the control room of the linear accelerator that was used to create element 111 and 5 of the other super heavy elements. The idea of this is that you have a metal target, usually lead or bismuth, elements 82 or 83, and you take a lighter element, say copper, and bang the copper at huge velocity into the lead or the bismuth, depending the element that you want to make. The idea is that you have to accelerate them very fast so that the two positively charged nuclei can come together, but not so fast that you have a lot of energy and they immediately fall apart again.
Okay, this is the periodic table of the elements that was used for the christening of element 111, which was called Röntgenium. And you see, you can remove this cube here. And Sigurd Hoffmann, the head of the group who discovered the elements, and our minister, Annette Schaman, together inserted the cube into the periodic table of the elements, and it actually started to glow. Oh, it was an amazing day. We had a huge ceremony. 1,000 people came here for the christening. Afterwards, there was cake and champagne, and it was really good.
Element 111 has a name which is really difficult to pronounce, Röntgenium, which is named after Röntgen, the discoverer of X-rays. I just find that it's a combination of letters that people in England find difficult to pronounce. However, Röntgen was, I believe, the first Nobel Prize winner, or one of the first Nobel Prize winners, and so it is really quite fitting that he should have an element named after him. The first discovery was of 3 atoms of this element, and then the experiments were repeated and another 3 were found. So it was still relatively quite a small number. But it's very important when somebody does a series of these experiments that you have to repeat them to make sure that you've really seen what you think you want. You're really excited, you want to make a new element. And so it's quite easy to fool yourself. Or sometimes people could be tempted to cheat. So you really have to repeat it. Ideally, you get a different lab in a different place using a different route. And if 2 people get the same results, you're pretty sure. But in this case, I think the 2 runs were repeated here. And it was still a whole period of 10 or 12 years between the discovery of the element and it being finally named, because people want to be absolutely sure that the data are correct. The machine that makes these ions is enormous. And it takes a whole team of operators to control it. And all this stuff behind me is to control the power, the voltages, and so on the different parts of the accelerator that takes the ion beam to this tiny chamber. It's really only about this size, where the actual experiment took place. And once the atom is made, it then flies off to the detector that's 2 rooms away down a long tube.
Yeah, of course, we are waiting now for the final confirmation to christen element 112, which is going to be copernicium. But, well, we don't know yet what we're going to do for the christening. We are having discussions what we're going to do, and I think it will be a big surprise.